All right, I think we better start. So it's my great privilege to introduce Shavani Naicker, who is a PhD student. She's on the point of submitting a thesis, and she will be speaking on this particular topic. I just need to make an aside here that the university now has introduced this rule that when you're submitting your degree, you've got to have made presentations. So all PhD students, even postdoctoral fellows, will be getting a request from us to make a presentation. You haven't received one, but you will be getting this love letter in the email at some stage. So everyone's. That's a requirement of the university. Now, Shavani, what can I say? She's been an excellent student, working very hard. She's produced a number of research papers in top journals, and she's received many awards. Most recently, she received this National Woman in Science Award. So she treats her work very seriously. Thinking about what to say about her, perhaps I should just mention very briefly three of her likings, things that she liked. The first thing that she liked a lot is entertainment. She liked singing, she liked dancing. She would be into conferences that we attended. You would find she's an active participant in these karaoke sessions. The other thing she likes is travel. She travels a lot. And in fact, much more than I do. She's been to many international conferences. She lived here, and recently she was in Heidelberg. She was one of those PhD students elected nationally to attend this Heidelberg Laureate, where you meet all the Nobel laureates. Third, I think is intention. You mentioned. She comes across as very relaxed, laid back, etc. But she took some time to work something out because she always seems to be in a hurry. She's hurrying here, hurrying here. But eventually I worked it out. There's a person called hurry. If you're going to go in a fresh, you'll find out. So over to you.
Can everyone hear me online? So it gives me a great pleasure. Class is known as Lovelock gravity, which is another form of Einstein-Gauss-Bonnet. And I will introduce background concepts in E2D gravity, which is a type of Lovelock gravity, and the foundation for modeling the interior of stars in the frame of gravity is provided. So my presentation on the following publications is on isotropic particles, and then extending this work to electromagnetic field in charge with a higher order gravity. 1915, Albert Einstein proposed a theory of general relativity that describes gravity and the curvature of space-time. It represents a unique marriage between matter and space-time, in which space-time tells matter how to move and matter tells space-time how to curve. So this theory then represents a foundation for analyzing the nature and behavior of gravitational fields of stellar objects such as stars and galaxies universe. So this coupling of matter and space-time curvature can then be expressed by physical systems known as the Einstein field equations in general relativity, described by equation here. On the left, we have curvature terms, and on the right, it works. Then, stellar structures. So general relativity is a successful theory of gravity, and it has been evidenced by gravitational bending of light, the Perrine reflection of Mercury, gravitational waves, and black holes. So it is then interesting to consider investigations in modified gravity theories, as general relativity is itself an extension of Newtonian gravity. So it's useful to consider its own extensions. Common gravity is a type of modified gravity, which is an active and exciting research area first introduced by David Lovelock in 1971. So this theory then natural extension of general relativity to higher dimensions, dimensions greater than the standard form. And it retains some of the characteristics of general relativity. For example, the equation of motions are up to second order in the metric potentials. The energy conservation is preserved, and pathologies like negative energy density are avoided in this gravity.
Double tap to exit. It's probably stuck.
Lovelock gravity. Here is Einstein-Gauss-Bonnet gravity, which is order 2 of gravity. So in this framework of gravity, curvature terms which are static. Now, several significant results have been considered in EGB gravity in various astrophysical scenarios, for example, gravitational collapse, black hole physics, and strictly symmetric matter distributions. So in the literature, some examples, we have the Bohr and Lisa 1985 solution, which is the high-dimensional static vacuum solution and represents the EGB analog of the Schwarzschild exterior solution. We have generalized Baudrillard-type solution in EGB gravity, which was generated by Kobayashi in 2005. This is the radiating type solution. And currently, some significant results in gravitational collapse have been considered in Russell et al. 2019 and 2018 in 5 dimensions and in higher dimensions. So it's found that collapse dynamics differ significantly from the 5-dimensional counterpart and the high-dimensional counterpart. And the work was then extended to look at the electromagnetic field in Russell et al. 2022. So some static strictly symmetric models have been considered in 5 dimensions and in 6 dimensions by Hansraj et al. 2015, Marad et al. 2015, and Hansraj et al. 2020. So these solutions represent the interior solutions, and in this work, we want to generate exact solutions for 3D symmetric models in a high-dimensional setting. So we're looking at dimensions greater than equal to 5. So we look at a neutral distribution as well as a charge field distribution. Okay. So an action will generate the field equations in any gravity theory. So in EGB gravity, we have the Gauss-Bonnet action defined by equation 2, where G there is the determinant of the metric tensor. We have R here being the Ricci scalar. This is the cosmological term, which we set to 0 for this work. This represents the alpha represents the Gauss-Bonnet constant, and this represents the Gauss-Bonnet term. So N here is the space-time dimension. So if we vary the action with respect to the metric tensor, we are able to get the definition of DC field equations represented in equation 3. So JD here is the Einstein tensor, which is defined in terms of the Ricci tensor RAB, the Ricci scalar, and the metric tensor GAB. We have alpha being the Gauss-Bonnet coupling constant, and HAB is the Lovelock tensor defined by equation 5, with the Gauss-Bonnet term defined by equation 6. So these equations are the higher order contributions arising in this framework of gravity, and they are quadratic in the curvature terms. So kappa here is the gravitational coupling constant defined in dimensions by equation 7, and when it is defined, so this is when gravitational constant G and speed equation 3 then couples matter and space-time curvature in EGB gravity. And when we set alpha to 0 in equation 3, we get gravity. So for our model, we will look at a static space-time that is of spherical symmetry, and it is defined in n dimensions by equation 8. Now, the gravitational potentials are mu and lambda that are functions of r, and we have this n minus 2 here denoted by equation 9. So just to see what the space-time looks like in a type of dimension, we look at n equals to 5, which is the minimum space-time dimension in EGB gravity. It takes on the form of equation 10. So we are considering the dynamics of a neutral fluid distribution. So therefore, the energy momentum tensor of such a fluid is defined by equation 11, where O here is the energy density, PR is the rate of pressure, and P theta is the tangential pressure. So equating the matter terms to the curvature terms, we obtain the EGB field equations for a neutral field distribution defined by system 12, where primes denote differentiation with respect to the radial coordinate r, and alpha hat is defined as alpha into n minus 3n minus 4. So these equations then describe the gravitational dynamics of the neutral field distribution in higher dimensions, so n greater than or equal to 5. And this system represents a system of 3 equations with 5 unknowns being the energy density, the radial pressure, the tangential pressure, and the gravitational potentials. So what we can see about the system is that there are several terms provided in green here, which indicate the higher order contributions arising in EGB gravity. And furthermore, we see several n minus 5 terms appearing here, and n minus 5 and n minus 6 term appearing, which tells us that dimension will have a significant effect on the gravitational effect. So we want to simplify this system. So to simplify the system, we use the Dirichlet and Bonnet transformation defined by equation 13. So now the potentials are y and z that are functions of x. And rewriting the field equations in terms of these variables, we have system 14. So here dots represent differentiation with respect to x. Again, we see that there are several terms which indicate the higher order contributions. So if we set alpha hat to 0, we obtain the general relativistic case. And this system is then provided by system 15. So field equations in the general relativistic case is represented by system. So we can see how the higher order curvature terms add to the complexity of the system. So now we want to analyze the gravitational dynamics neutral fluid distribution in each gravity. So we want to equate the radial pressure and pressure, we get the condition of pressure isotropy defined by equation 16. So this equation represents the gravitational behavior of our model, and it is classified as a second order linear differential equation in y if the potential z is 1. So we can see that again, several terms in green indicate the higher order contributions. And this equation has been studied in 5 dimensions and 6 dimensions, respectively, by Hansrod et al. 2015. So it's important to solve this equation for the potentials y and z in order to obtain expressions for the energy density, the radial pressure, and the differential pressure. So to do this, we rewrite it in alternative form, represented by equation 17. This equation is now a first order nonlinear differential equation in the variable z. Its y is 4. And it is further classified as an Abel differential equation of the second kind in z. So these equations are quite complicated to solve in general, and no known general solution to this equation. And we see several n-5 terms appearing, which tells us that when n equals to 5, there is some simplification. So then the condition of pressure isotropy takes on the form of equation 18, still an Abel differential equation of the second kind in Z. However, solutions to this equation were presented in an ad hoc manner by the following in the literature: Chilamba et al. 2015, Strike et al. And Marat et al. 2015. So we can see that several terms in green indicate the high order contribution terms. And when we set alpha hat to 0, we obtain the Einstein case. So just to see the differences, I set alpha hat to 0 in this equation. And now we have a first order linear differential equation Z to solve. So in the AGB case, the condition of pressure isotropy is an Abel differential equation of the Z. However, when we look at the I, have a second order, first order linear differential equation in Z. So the higher order contributions complicate the condition of pressure isotropy. And solutions to this linear first order differential equation have been illustrated. In 4 dimensions by 1998 and in 5 dimensions by 1988. It's n greater than 8. Okay, just to recall the Abel differential equation. So what classifies the center is due to the presence of the ZZ term appearing, this Z squared term appearing, this Z term, and this inhomogeneous term appearing. So that's what classifies a condition of pressure isotropy as an Abel differential equation. So we need to solve the equation for the potentials y and z in order to obtain forms for the electric field, for the energy density and the pressure terms, which is very useful. So we then demonstrate solutions to this complicated equation by transforming it. So we transform this equation using the variable. So using the variable, small w defined by equation 31. This was illustrated in Pollyanna and Bateson, 2003. So now capital W is defined as an integral defined by equation 2. And we have the following restrictions. N has to be greater than or equal to 5. Alpha hat cannot be 0. And this term here cannot be split. So the Abel differential equation of the second kind, using this transformation, reduces to a canonical differential equation represented by equation 23 in terms of the new variable W. So it's interesting to see that a complicated nonlinear differential equation, the Abel differential equation of the second kind, reduces to this canonical form in 23, which is the first order and nonlinear differential equation in W. And we have introduced the functions f1 and f0, that depend on potential y and its derivatives. So the functions f1 and f0 then have the expressions 24 and 25. And as we can see, they depend on the potential y and its derivatives.
Good fast.
We
Imagine you having an argument with Rick.
So this first seeing the functions f and f depend on potential y and its derivatives in a complicated manner. So in general, it's difficult to solve this equation. So we now demonstrate solutions to this problem by choosing the potential y as x. This choice was considered in the study by either 2020 for the particular space and dimension getting this. So now capital W can be evaluated, the integral in capital W can be evaluated, and we obtain the expression simple form of 1 over x. Then the first order nonlinear differential equation W in equation 6 then reduces to the form of 29. So now the functions f1 and f0 depend on the variable x only, and it's a simpler function involving variable x. So now we can demonstrate solution to this equation in its form. Even though it's first order and nonlinear, we further make substitution defined by equation 30. And then we have a separable differential equation 31. So this is quite remarkable that we are able to solve first order nonlinear differential equation using the substitution leading to a separable differential equation that can be integrated. So if we integrate this, so integrating the separable differential equation, back substitute to obtain in terms of the variable W by equation 33. So now this equation is a sixth order polynomial in the variable W, and it has 6 roots. And in general, it's difficult to find roots of the sixth order polynomial. So we can then factorize it as equation 34. So we can now find the roots of this equation, and solving for W, we have the 2 real roots represented by equation 35. So this then solves the canonical differential equation in terms of W for all spacetime dimensions in relativity to 5. So since we have solved this canonical differential equation in terms of W, we can now back substitute using the transformation to obtain the potential Z. So using the transformation again in 36, with y being the square root x, and capital W defined as 1 over x, gravitational potential Z can be found and is expressed in terms of equation 37. So this potential Z is provided in an explicit form, expressed in terms of elementary functions of x, which is very useful for stellar modeling. So this solution, gravitational potential Z is 37, and the potential Y as square root x, then solves the isotropic pressure condition equation, which is the Abel differential equation. And we were able to solve the Abel differential equation of the second time by transforming it first. So it's important to see that the potential Z has no general relativity, and we cannot set alpha hat to 0. So we can then demonstrate special cases of this potential Z, looking at any. We have the solution 38, which appears to be a new solution not containing Euler treatments, and any potential Z 2020 or now we can demonstrate canonical differential equations without specifying y or z. And to do this, we will place constraints on the canonical differential equation. So we are able to do this in 3 classes of solutions. The first case, we set f1 to 0, which yields a constraint 40. And the canonical differential equation, a first order nonlinear differential equation, reduces to the typical differential equation 41. And a complete solution can be found if the potential y satisfies this constraint 40. In case 2, we set f0 to 0, and this yields the condition 42, for which the canonical differential equation again reduces to a separable differential equation of the form. So complete solution can be found if potential y satisfies the constraint 2. In case 3, we have f1 being proportional to f0, where k is some constant, and the canonical differential then reduces to form, which is again a separable differential equation. So in all 3 cases, the first order nonlinear differential equation formula reduces to a separable differential equation. And we were able to obtain these results by placing constraints on functions f1 and f0. So the most interesting of this case is case 1. So case 1 is when f1 is set to 0, the function, and this leads to the constraint 46. So it's interesting to see that this equation is actually a product of a first order and a second order linear differential equation 1. So with this constraint, we can obtain 2 classes of solutions for 1. In the first case, we solve the first order linear differential equation in y, represented by equation 47. Now solving this leads to the solution 48. Now we can solve the separable differential equation in w, back substitute, and obtain z defined by equation 49. So this is defined for all space-time dimensions n greater than or equal to 5 and is expressed in terms of elementary functions of x. In the second case, we need to solve the second order linear differential equation in y, represented by the following equation here at 50. And solving this, we obtain solution 51 for the potential of y. Then we can solve the separable differential equation in w, and back substituting using transformation, we obtain the potential z in expression 2, which is again expressed in terms of elementary functions of x. And we can see that these classes of models arise due to the transformation. And furthermore, we do not have a general relativity, but in this case, so it is interesting to generalize these to look at the electromagnetic field. So we include the effects of the electromagnetic field, look at the the dynamics of a charge fluid distribution. So our fluid is now in terms of electromagnetic field. So the EGB field equations and Maxwell equations are represented by the following system with the energy momentum tensor of a charge mass distribution defined by equation 4, with the electromagnetic tensor defined by equation 5, and the surface area term defined by equation 6. So when n equals to 5, it has a form of 2 pi squared. So the electromagnetic potential is then defined by equation 7, with phi being a function of r as the gauge potential. The Faraday tensor is then defined by equation 8. So we can then obtain the non-zero Faraday tensor by which set energy. Now equating the curvature terms to the lattice terms, we obtain the charge EGB field equation defined by system 63. In terms of the variables x, y, and z. So this system then describes the gravitational dynamics of a charge fluid distribution in EGB gravity for n greater than 4. And now the terms in orange represent contributions from the electromagnetic field. And we still have a term in green representing contributions from first terms in green. So once again, as concerned in the neutral case, we will assume isotropic pressure equate the radial pressure to obtain isotropic pressure condition in 64. Now in the presence of the electromagnetic field. So again, it is classified as an Abel differential equation of the second kind in Z if the potential Y is. So even though we included the effects of the electromagnetic field, the form of the equation does not change, and the Abel differential equation still arises. So this equation then represents the gravitational behavior of Abel, and we need to solve this for the potentials Y and Z and the electric field intensity. So we can see that if the electric field intensity E is known, then the condition of pressure isotropy, which is an Abel differential equation, has to be solved to have Y and Z. However, if we specify Y and Z at the beginning, then we can obtain the electric field intensity without any integration to this equation. So we can demonstrate solutions to this Abel differential equation as considered in the neutral case. We look at the same approach. We transform it using the variable W represented by equation 65. Capital W defined in equation 66. The same as the neutral case. We have the following restrictions working once again. Then the Abel differential equation reduces to canonical form 67. So it's interesting to see that even though charge is present in our study here, we're able to transform the Abel differential equation of the second kind to a canonical differential equation 67 in terms of the variable W. Now the functions f1 and f0 depend on the potential Y and its derivatives and the electric field intensity, which have the expression 68. So we can demonstrate where the x function and now we choose the electric field intensity defined by equation 2. So A is some arbitrary constant. Then evaluating the integral with capital W, we obtain the expression 63. So the canonical differential equation using 71 and 72 is now represented by equation 74. So we have the functions F1 and F0 defined here in terms of the variable x. Now in the presence of the electromagnetic field. And when we set A to 0, we regain the neutral case. So we can show solutions to equations and four by further making use of the substitution 5, which again leads to the separable differential equation 6. So we can integrate this, and this yields a solution. So that's substituting for W and consequently the potential Z. We have a solution, the gravitational potential Z, find in equation 17. So now this potential Z is in an implicit form, and it is defined for all space-time dimensions and greater than equal to 5. There is some significant differences in the neutral case and the case when we look at the electromagnetic field. So when we set A to 0, we regain the uncharged case, and the gravitational potential Z is provided explicitly. However, when charge is present, we have an implicit solution for the gravitational potentials. And again, there is no general relativity counterpart to the solution. So if we set A to 0, we once again regain the neutral solution for the potential Z, represented by equation 7. So we can now demonstrate solutions to the current equation without specifying the potentials y, z, or e as done in the neutral case. So in the first case, we look at f naught to be 0, which yields expression 81. And with this expression, we can then obtain a general form for the electric field intensity E, represented by equation 82 without integration. So it's interesting to see that in this class model, we're able to obtain the electric field intensity without integration. And we can obtain a complete solution if we substitute for a potential y equation. So then we back substitute and we have the potential Z represented by equation 85. So this tells us that we have a general expression for the electric field intensity without integration, and the potential y, any form of potential y solution. And so that as done in the neutral case, leading to the potential. Now in this case, we just need to choose the electric field intensity, and the potential y is given by two classes of forms defined by condition F1. So it's important to see that these classes of solutions do not arise in setting. So to conclude, we have investigated static spherically symmetric models in a higher dimensional equilibrium setting. First, we looked at a neutral field distribution, which is an isotropic pressure condition equation assigned by equation 91. We're able to solve this using a transformation, and we are able to reduce it to the canonical form. It's interesting to see that a canonical differential out of the differential equation. This represents a solution generated algorithm which enables us to find exact solutions for the potentials y and z. And we are able to find exact solutions to this equation 92 by placing constraints on the function f1 and f0, and by choosing the potential. It's important to note that the classes found here for the solutions only exist in equilibrium. So then these effects were included to the electromagnetic field, and we found that charge allows for a greater degree of field, and classes of solutions were found which do not arise in the usual case. And the importance of this work has been considered in applications of astrophysical stars in following literature, and as a future work, we need to construct a complete stellar model by analyzing the gravitational conditions and the energy conditions. Thank you. And these are some references which I included in here.
Thank you very much for that, Shavani. It's one for the sake of questions. I just want to make a general observation. And when one is studying many of these nonlinear phenomena, you find that when you study these problems, you bring it down to some sort of canonical form, you find invariably you have the heart of the problem in the Abelian differential. You say other, I don't know what's like pronunciation. So it is at the heart of this Abelian differential equation. The remarkable thing is that the phenomena in very different settings come down to equations of this type. And unfortunately, that's one of the classes of equations with few standard distribution. That's the reason. But let me put it open for questions, comments. Yes, anyone?
The known but nice way.
Just, yeah. I thought there might be a question. This is an opportunity. Questions, comments? It's either that you confused everyone, or it's such a clear presentation that nothing left to discuss because of blah blah.
No, it's just spoke about theorem one. Chronology. Now, those marks open here. Just
Yes.
I agree. It says
Something concrete.
something concrete, solid. And the same with the chronology. I think those.
No, sir. It's a fair comment. If there isn't anything else, yeah. More. So, you have a question? Please, go ahead.
So, just want to know how might the solutions that you have derived from the static model influence our understanding of UF? And would these models be able to predict other or different general that could actually be?
Yes, so the solutions found, there is no general relativity counterparts. These models yeah. And
Perhaps I can add to that. It's a very, very good point. For it to be meaningful, you got to tie it down to astrophysical processes. And these expressions that you get for the potential, you can use to calculate mass. You can deduce radius, mass radius ratio, really important, the luminosity. And in the past, one didn't have the potential, and now these typically important quantities are being calculated. That's the next point. You need the solution before you can calculate. And then that's being done. And there have been some papers that have been recently published that are showing that we're getting distinct differences from there's two other points I want to make. We can interrogate the common room down the corridor. Please come along. Lunch should be available. Shavani tells me there's also, in addition, a surprise. I don't know what it is. It's a surprise. So we'll find out. So please don't run out. It's a surprise. So let's come to Shavani again.
And
So,